Okay, another go. So next we have Savio from the security group here in Eindhoven, and he will talk about identifying radio frequency devices via wireless signals. So, and I think he will talk a bit about the dark side of a general useful technology that allows also to spy on you.
Thank you. So I hope you can hear me out online. So thank you for the presentation. So today I will talk about one of the research areas active here at TU Eindhoven in the area of wireless security. So quite of a switch from the cloud perspective we discussed so far. We go more to the physical world around us. In particular, I will discuss about another form of usage of a technology that is more famous with the name of radio frequency fingerprinting, something that is a lot used as an additional security layer, basically for wireless devices, but it can also be used, looking at another perspective, as a way to threat the privacy of users by tracking basically the wireless devices in possession of the user. That's a brief agenda of what I will discuss about. And in particular, I start from the very basics, the radio frequency fingerprinting. That's a research domain that was born around the 90s, 95 of the previous century, but at the boom starting from approximately 2010, when it was clear that it could be possible to use it, especially with respect to constrained devices. And then finally, 2015, with the introduction, basically more in the general public, of deep learning solutions that make it possible to identify basically devices based on their features, but in a range of different scenarios. Where does it come from? Basically, the idea is that normally in your wireless devices, in your commercial off-the-shelf devices, you have these chips that you see here in the slides. And this is what you see of your wireless chip, nothing else. But there is a lot happening inside of the chip after you give basically through your host the bits to this radio chip for being transmitted. This is what you have basically inside your chip. These circuits that you see here that are basically hardware circuits, you can implement it in principle both in software or in hardware. However, doing that in software is a lot expensive because you need devices that are able to process signals at very high frequency. So the usual choice that all the manufacturers make basically for cost considerations is to have all these circuits implemented in hardware. Basically, you see mixers, you see oscillators, phase shifters, a lot of different hardware components. All these hardware components that are done in hardware, they have their own inaccuracies. They are physically done to do a job good enough, and even when they are printed on the circuit, they have some small tolerances in the order, for example, of micrometers. Of course, these tolerances do not affect the capability of the device to operate as it should. They transmit bit, and they have approximately the same performance. But if you look at the signals that are transmitted over the wireless channel, there are very small differences, subtle differences that, although not impacting on the quality of the communication link, affect basically the specific way they are received at the receiver. Let's take an example. For example, a generic quadrature phase shift keying modulation, where you have 2 bits per symbol, 00, 01, 10, and 11, and then base for symbol. What you would expect, what you do software level, is to basically encode these, the 4 bits, to one of these four values. And you would expect to receive them at the receiver exactly the same. Surprise, surprise, that's not the case. Already, if you would have the possibility to see these at the transmitter, you will notice that you will have these clouds here, because the transmitter tries to transmit them with a given precision. But there is always an inaccuracy in the specific value that it actually transmits. It's not a 1, but it's a 1.0001. It's an imprecision that the particular wireless device cannot control because it's inherent in the inaccuracy, basically, of the hardware components of the device. At the receiver, on top of these inaccuracies originating from the transmitter, there is the channel. If you are lucky, you get the situation at the top right, where you have those clouds originally originated by the transmitter, plus some more noise, meaning that the channel is not that noisy. But if you are unlucky, for example, you take this situation that is the signal you receive, for example, from a satellite, you get very noisy signals. So your clouds that were originated by the transmitter now are completely, basically hidden in the noise. So at the receiver, in this case, of course, in the case here, right back, you have a problem also with the signal-to-noise ratio, with the bit error rate. But in general, if you look at above, then that configuration does not really cause problems in terms of quality of the communication. But at the same time, could allow you to identify who is the transmitter in a set of different transmitters. If you look at the situation that you have, for example, in a cable link, that's where what we call features of the transmitting device emerge very well. This is, of course, an ideal situation. It's just an example, because it's not only these features that that characterize the specific transmitters, but if you look at it in a diagram like this, you don't need any AI. With your naked eye here, you could tell among these 12 devices who is the one transmitting. So in a cable link, or when you are connected via cable, the task of identifying a specific device is very easy. The problem is when you go over the wireless channel, because the channel actually hits the specific features that you want to use to recognize the device. The security assumptions that normally are associated with the radio frequency fingerprinting are mainly two. The first one is that the profile of the IQ samples, the actual raw signal at the receiver, depends on the hardware of the transmitting device and the properties of the channel between the transmitter and the receiver. That's exactly what we discussed in the previous slide. The second assumption is that the transmitter has very limited control over the specific value of these IQ samples that are transmitted over the wireless channel. You can say to the device, you can tell to the device to transmit a 1. The device will transmit a 1 with a very small inaccuracy to the 6th or the 7 decimal digits that the device cannot control, but that can be used at the same time to identify the device. If these two main assumptions hold, then the radio frequency fingerprinting is possible, and the regular, normal way this is used, typically also a lot in the scientific literature, is as an additional security layer to the existing devices. Because basically you can identify who is transmitting without even modifying anything on the transmitter. You don't need any cryptography solution. You don't need any software specific on the device. You can do that completely passively by just analyzing the raw wireless signal that is transmitted by these devices. This is also very useful, for example, if your keys get leaked. Typically, you use cryptographic keys, for example, to do authentication. If your keys get leaked and another device transmits exactly the same signal, then looking at these hardware characteristics, you can recognize that it's not the device for which the key was originally assigned to transmit that message, but it's another device. And so you can do a form of basically physical layer authentication of the devices. That's normally how radio frequency fingerprinting is used. Of course, you need specific hardware available at the receiver side. You need an hardware that is able to go down at the physical layer to analyze the raw wireless signal transmitted by the device. And this is not something that you usually have in commercial off-the-shelf devices. There are some of them that may allow for you to do that. There are some Texas Instruments chips now that allow you to see the raw IQ samples. But normally what you will need is a software-defined radio. So it's a radio that is able, basically like a spectrum analyzer, to see the raw wireless signal and process the raw wireless signal. On top of that, due to the availability of basically to the presence of the wireless channel that could complicate the detection of this feature, what you need is also some powerful hardware that can run some deep learning algorithm, and so it can tell apart basically the features of one transmitter with respect to the other. They are a bit what we call the requirements, or if you want to call them the constraints, of using this as an additional security layer. There are a lot of software-defined radios available. There are even some small dongles that were used originally for receiving TV signals that were hacked and can work as a software-defined radios. And they are available on the market on Amazon, for example, for as low as 20 euros. So not necessarily you need an hardware like the ones that you see here that is significantly expensive. You can do that also with hardware that is not that powerful. There is a lot of research on radio frequency fingerprinting from a lot of research groups all around the world. And this is mostly about using this as an additional security layer. You can see just from these titles that this has been applied to satellites, to IoT devices, to drones, even to aircrafts to recognize which one is that. So different technologies, different communication paradigms. Today, this is really used. We are also, as a research group in this area, we applied this, for example, for the satellites. And we have also some ongoing research at UE on this area, using RFF as a security feature. For example, we investigate real-world factors that impact your accuracy to do radio frequency fingerprinting. We discovered, for example, that simply power cycling the devices changed the fingerprint of one device. And in some devices, even reloading the firmware changes that fingerprint a bit. Based on that, we were able to discover basically, or to come up with models that are very robust to small variations basically triggered by these embedded systems. This is the angle of the problem, more of using radio frequency fingerprinting as a security feature. However, if you are a little bit, let's say, familiar with the security and privacy aspects, you may also have noticed that this can also be used on the other way. If you have a now unauthorized receiver, an eavesdropper can collect the wireless emissions of the devices in the wild, then train a model based on you and be able to recognize your device when it's present in the given reception area of the device. So this motivated some of our efforts to go into the other direction, basically flipping the problem and say, can radio frequency fingerprinting be used as an attack vector to track the devices in the wild? We have some preliminary research more on the attack side. I will not show that in the slides. That basically shows you that if you are able to collect the profile, the raw wireless signals of the device at different locations in a given area, then by training on all these samples on different locations, your capability to track the devices, even in different locations in the same area of that particular device, is possible. Of course, that requires some more computational capabilities, but in general, the threat is possible. And the specific threat can be configured in two different ways. The most powerful adversary model that you can think about is an adversary that knows the RF profile of all the transmitters in a given area and can then track each of them by telling this device apart from all the others that he knows. This is the most powerful adversary model you can think about. What in the rest of this talk basically will be called as A1. Another possibility is that the adversary only knows one profile of one device and tries to follow this device in a range of, in an area where there are different devices that it doesn't know. You need different techniques, different attack vectors to do that. You need, in the first case, a multi-class, basically, classifier, while in the other case, you need a one-class classifier because you know only one device. But the two attacks, technically speaking, they are possible. So this is the main threat that we considered. The problem is that if you want to mitigate basically this tracking, you have to take into account what each wireless device or normal wireless device can do. You cannot really tell to this device to change the fingerprint, or you cannot install software on a mobile, for example, to change the profile of the emitted device, because that will simply not happen. The software of the device does not control or minimally control, as we have seen, the hardware of the device. So you cannot basically modify or impose physical layer modifications to the transmitter in the general case. At the same time, you also would like to keep the communication performances of the devices the same. So you don't want to degrade the signal-to-noise ratio that you experience at a given receiver, and more importantly, the bit error rate. You want to continue transmitting with the same performances. You also have to consider that whatever you do, the adversary could be able to adapt. So when you do some modifications, the adversary could be able to retrain the model, and then based on this new model, let's say, model of your emissions that you have created, keep tracking the devices. That's something that can be done in both the adversary models. In particular, we defined two concepts basically to work with that. One is the traditional K anonymity. So you want to identify one in a set of K, and T anonymity when you want to be anonymous independently of the set of transmitters that are in a given area. Taking into account all these constraints that the problem have, we basically investigated with a first solution to this problem that we called finger jam, that is basically about deploying a low-power jammer, so an external device, basically, close to the device that you want to protect. This jammer is basically what is more famous, let's say, as a friendly jammer. So is a jammer that injects just a low power to thwart the radio frequency fingerprinting, but not to affect the quality of the communication link. It's just a low power noise, basically, that is not affecting the quality of the communication, but affecting the shape of the signal that you receive at the receiver. You have to deploy this jammer close to the transmitter, of course, because you don't know where the receiver is. And the challenge is to basically understand if this works, if you can really thwart the radio frequency fingerprinting without affecting the quality of the communication link. That's the main idea we experimented with. To the same, we have a lot of results based on a real deployment campaign that we did. In particular, the results that I will show you now are based on 5 different transmitters that we deployed in an office environment. So in a normal environment with interferences already occurring because there are many devices already there communicating, we used one receiver. The radios that you see here in these slides are radios that are particularly powerful. They are the USRP X3010. And we used 2 main communication links. One is a cable link just to understand the impact of our phenomenon, the impact of how the jammer affects basically the radio fingerprints. And then for the other experiments, we use the wireless channel. Most of the results you will see are based on the wired channel, the cable link, because we wanted to understand really what are the boundaries between fingerprinting and not fingerprinting the device, and then the other, let's say, results more in the wild with the wireless channel. To control better the deployment, to fine-tune the intensity of the jamming we were basically injected into the wireless channel, we used also attenuators. Attenuators that are on the jammer, 20 dB and 40 dB, so a small attenuation and a more significant attenuation. And we changed also the power of the signal injected by the jammer. You see here that there are different relative transmission power that you can use on the jammer. So 0.01%, that 0.01 means 1% of the overall power available on the jammer, up to 100% of the power available. So we experimented with different, basically, power levels. First, we did an analysis of the, let's say, impact of the jammer on the quality of the communication link, in particular by looking at the SNR. You see on the figure on the left that in general, as you would expect, by increasing the power of the jammer, the quality of the communication link between the transmitter and the receiver basically decreases. That means that the signal-to-noise ratio is decreasing. The challenge here is not to decrease the signal-to-noise ratio up to the point that it decreases the quality of the communication link. So the lines that you see on the right part of the figure, the violet one, the cyan one, the blue, they are affecting the quality of the communication, something that you don't want. Instead, the green and the black ones especially, they are minimally affecting the quality of the communication. They cause small variations with respect to not having any jamming. So they are the ones basically where we focused more because they don't cause any drop in the quality of the communication. You also see in the slides on the right that in general also the attenuators can further attenuate the intensity of the jammer and keep the signal-to-noise ratio more close to the one that you experience without any jammer. So we focused more in that region because that region didn't cause any drop in the quality of the communication. We started with a benchmark, so the traditional radio frequency fingerprinting, but without jamming. For example, in the scenario of k-anonymity. So here there are a lot of techniques that you can use to do radio frequency fingerprinting. The ones that we used for this particular work, they were the ones that we refined through analysis of different, let's say, phenomenon that can happen in the real world. For example, the reload of the radios or the changes of the channel. So techniques that are already known to be particularly robust to changes to the channel. They're also techniques that are likely to be able to be basically used by the adversary to do actually the tracking. Based on those, basically, we transformed the problem into a classification problem where you classify images based on a set of signals that you receive, and then the problem becomes basically an image classification problem that can be done, again, multi-class or one class based on the training set that you have. You see here, especially in the figure on the upper part, that independently from the specific network, multi-class network that you use, the task is always feasible for the adversary without jamming. You always have classification accuracy that are basically very, very close to 1. They are 0.99. So this confirms in general that these techniques, these classifiers, are able to identify the wireless devices without any noise added to the transmissions. Starting from this point, basically we added through the jammer through the actual experiments on the wireless cable, we added noise, and so to how much extent, basically, the classifier is still able to identify the transmitters. You see in this figure the results on the cable, basically, where we increased the relative jamming power of the jammer, and you see that, as you would expect, by increasing this jamming power, the signals that are received by the receiver are different. So the performance of these models start to decrease. The interesting result is that you need a relative jamming power of 0.3, as you see in this slide, to completely transform the output of your classifiers, basically, in a random guess. 0.2 here because we have 5 transmitters. So over 5 transmitters, the random guess is 20%. So only a relative jamming power of 0.3 it's enough to have random guess. That relative jamming power of 0.3 at the same time affects the signal-to-noise ratio and the bit error rate. So the actual challenge is to have these two parameters, to basically trade off between these two parameters. You have that trade-off approximately at 0.1 jamming power, as we have seen in the previous slide, and there the classification accuracy, depending on the classifier that the adversary is using, is ranging between 0.6 and 0.4. That starting from 1 could be, from some scenarios, something already acceptable for some scenarios. It depends a little bit on what your target is in terms of protection against the devices. We also experimented with the other attack scenario, the one weaker, let's say, that is the case where the adversary only knows one specific device and tries to identify that device in a range of wireless devices. Basically, what we investigated here, we used an autoencoder as a one-class classifier. So the task is classifying images coming from the same transmitter. What you see here is that, first, the random guess line. The random guess line, it's basically the diagonal of this graph, the main diagonal. And it means that any point basically lying on this is indistinguishable from the model on which we trained. So the two models are the same. The more the curves or the samples go toward the upper part of the graph, basically the more the two profiles are distinguishable. And so the adversary can tell apart that particular transmitter from another one, or that can identify basically the two devices. You see that with 0.1, 0.2, 0.3, we get a bit away from the diagonal, but it's with the other ones that you make the two devices completely different one from the other. So by adding noise, basically the, let's call new signal, the testing signals, becomes increasingly different from the one that you have during the training. We also experimented with different attenuators, so 0 dB, 20 dB, 40 dB, with the requirement that all the signals we are further processing have the same bit error rate of the ones we experience without jamming. So all the signals that we have are characterized by that condition, no bit error rate. As expected, the less the jammer attenuation, so the higher the jamming power, the more different the radio fingerprints are. And so the accuracy of the radio frequency fingerprinting is basically reduced. That is what we want. We want to transform this problem for the adversary in a random guess. We also went to the radio link. So we did the same experiments, but on the radio. We collected first the signals from the devices, and then we tested it on signals that are basically affected by the noise inserted by the low-power jammer. Again, the same considerations that we had before. The low bars are the ones basically with the jamming power 0, while the higher one are with the jamming power 1. The two different profiles are completely different, although being characterized by the same bit error rate that you experience without jamming. Of course, to do that, you also need an attenuator, because otherwise the power is too much and degrades the quality of the communication link. This is, let's say, the easiest scenario, the scenario where the adversary cannot retrain his models. But the adversary can also be basically adaptive. So when it starts to understand that his performances are decreasing, it could dynamically retrain the models and try to update his models to follow this new profile of the emissions of the devices. And that comes the challenge. In the most powerful scenario, the scenario where the adversary knows all the devices, you see on the left that when the adversary trains on all the different power levels, then his performances remain very high, even if you increase the relative jamming power. So basically, considering the most powerful adversary model, the adversary wins, is able to continue track the devices. When the adversary instead, and I focus on the figure on the right, only knows one particular device and tries to update the model, then his task becomes a little bit more difficult. There are some devices, for example, you see the device number 4, that are completely distinguished from the other devices. So in that case, for the device number 4 in these tests, the adversary can be still successful because it has basically a classification capability very close or in sometimes even higher than the 90%. There are other devices instead that become more similar to others, and so they are less distinguishable with themselves. You see, for example, device number 2 or device number 3 that are characterized by lower accuracy. So those are less distinguishable even after adding noise from other devices. So the solution, to a limited extent, could work in that scenarios. But that, of course, depends on the specific transmitter. So you have no guarantees that a solution like this would work. And this is exactly basically the starting point of the final considerations after all this discussion. So radio frequency fingerprinting in general, it's something that it's possible to be used on the other way, in a powerful way, independently basically from our solution, but it's possible to use it to track in the wild wireless devices. Protecting against such a threat is not really straightforward because you have the constraints of commercial devices. You don't want to touch as much as possible these devices. The solution we experimented with in these results that I showed you is a solution where you use a low power jammer to externally, without modifying the device, try to protect its privacy. It works to a limited extent. It can work based on the device if the adversary only knows one and tries to follow you with that one. But if the adversary knows everything, as we saw in the previous results, basically it doesn't work. If it knows everything and is able to retrain its models. This is also basically an acknowledgement to the power basically of these AI algorithms that are able still to recognize the device, although their emissions basically are hidden in significant amount of noise. What's next? Basically, the road ahead that we are still investigating, we started to do that, is to see if by having the possibility to inject noise on the transmitter side, we could be more lucky. So what if we have a transmitter that is able to corrupt intentionally a little bit its signal? Does this improve the situation compared to having an external jammer that can do that? Of course, that would require a complete change of the hardware of the transmitter. That's something that, of course, should be taken into account. But maybe we are more lucky on this side. And the partial results that we have from another work that is not the previous one, that I discussed, is that it seems that when the transmitter intentionally corrupts the signal, then it's really more successful to thwart the adaptive adversary, even if he knows everything. You see from these initial results taken out of the reference paper that is still submitted and under review, that the false positive and false negative in a range of transmitters is quite significant, between 0.2 and 0.4. So identifying the wireless devices, if it is the transmitter itself to inject noise, seems to be more difficult than when you have an external jammer deployed to protect the privacy. However, this is all work that is ongoing, but in general denotes how much difficult is it to protect against these attacks that work on the physical layer. For the ones interested here, you see some references of the work that I mostly focus, that will be presented in August in Asia CCS in Vietnam, and other works of our research group, basically on the area of radio frequency fingerprinting. I'm happy to take any questions from the audience. Thank you.
Thanks a lot. Are there any questions?
So how much signal do you need actually for this fingerprinting? It's really little, I guess, or?
There are approaches that can take only the either of the device, basically, and fingerprint based on that, the either of the transmitted signal. Because the either typically is the part that is always the same in the signal. So that's what is used basically to characterize the device. If you look, however, at the usage of radio frequency fingerprinting on the other side, you can take the whole signal, basically, because that is characterizing the actual device. So the more data you have, the higher the performances are. But there are approaches that can work even with very small data.
Hey, thank you for your talk. You said that the attacker has to use a different piece of equipment to do radio frequency fingerprinting. Is this a different equipment, or is just a better quality receiver?
Yes, so it is I think the right word is a specialized equipment. It's an equipment that is able to extract the raw signal at the physical layer. Normally, with commercial off-the-shelf devices, you don't get that. You get directly the bits of the signal. You don't see what is happening at the physical layer. This device is the software-defined radios, or there are also some chips now by Texas Instruments that are able to do that. They give you the physical layer representation of the signal, what in the talk was referred to as IQ samples.
Hi, great talk. Are you familiar with the work of the late Andreas Fitzmann and the anonymity world in Germany that was working on radio fingerprinting for anonymity purposes, where they were hoping that everyone could have universal radio transmitters, and then they were heartbroken to find out exactly what you're talking about. Everything is unique.
Not sure about the work you refer to, but we can look at it.
And have you looked into cross-protocol analysis? For example, almost all phones, when you unlock them, because of things like Apple and Google Pay, they broadcast unique identifier for the phone, and even if the device is powered off sometimes. And then you have things like Wi-Fi MAC addresses and Bluetooth MAC addresses. And have you thought about trying to fingerprint like the set of signals from a given device so that you can make a profile even of the type of device based on what it does?
Yeah, so this talk was specifically focused on the physical layer, the raw signal. I believe the information you are talking about is a bit higher in the protocol stack, is at least MAC layer, if you talk about identifiers all that kind of stuff. So you can see this as an additional attack vector or an additional information available to the adversary with respect to having that information. Yeah. Still there.
Hi. Is it possible for the attacker to impersonate another device to forge the fingerprint?
So there is some research on that. Basically, with commercial off-the-shelf devices that are typically designed to be low cost and cheap, no way you can do that. There is some research showing that if you use a very specialized equipment with very high performances, you have chances of impersonating the device. That equipment, as of today, costs $100,000, something like that. So let's say the common assumption is that if you have a very powerful adversary, yes, it can impersonate, for example, a nation state or something like that. It can impersonate the devices. If you have in the wild normal commercial off-the-shelf devices, that's not viable.
So my question earlier, when I was talking about multi-layer, I probably should have made it more clear. You have N transmitters on a device, right? Each transmitter has its own IQ sample that it's going to emit. And so what you can say is you've got the RFID transmitter when you unlock it. At the higher level, you can interpret that, obviously, with the identifiers. But then you also have continuously broadcasting Bluetooth, often Wi-Fi probing. And then you have the EM emissions from the device itself because it's not very well shielded against like Tempest-style attacks. So my question was, do you consider the set of all the transmitters, or are you really thinking about it on a single radio by single radio device? Because it seems like if you're jamming, say, the Wi-Fi in 2.4 or 5 gigahertz, but then it's actually not jamming the RFID signal at the same time, then you're going to see, relative amplitude and so on from all of those radios, and you'll see exactly one of the layers being jammed.
Yeah.
And so I wonder, are you doing basically wideband spectral analysis to fingerprint all the radios on the device?
So now I understand the question. Thank you. So in this work, we consider only one transmitter, one radio. Of course, if your device is characterized by multiple transmitters, each own with its own communication technology, you will need basically a low power jammer for each frequency basically where the device operates. But this work considers only one transmitting radio, one antenna.
Have you looked at the sensitivity of the classification when you change receivers? If you want to track, I think ideally you have a network of receivers to see where the device pops up physically. Have you looked at it?
Yeah, so in the context of this particular work, no. But there are, and we also did it, some works where we applied, for example, radio frequency fingerprinting to identify satellites, LEO satellites of a satellite constellation. And to avoid this problem, to basically take out the receiver in the fingerprint, we did deployments at several locations. So we avoided the location with different receivers, and it worked. So it's in the end, it's about how you train your model, but the model can be trained in a way to be completely agnostic, independent of the receiver and the channel.
Have you considered the influence of temperature changes on the quality of your measurement?
Thank you. For this particular work, no. But there are works that look at that, that have demonstrated that, especially for some specific devices, the more they heat, this changes the fingerprint. These works, however, have also demonstrated that you can remove that effect and build a fingerprint that is basically independent of the temperature. All these works that I'm saying, also the other one, they have been all conceived considering the additional security layer. So you can reverse it, and they apply also on the other side to track the devices. So it has been done, not by me, but there are works that do that.
I'm sorry, the last remaining questions we will have to take offline. We have a coffee break now, 30 minutes to take questions offline, and then please be back in the room in half an hour, and let's thank Savio again.